What is a differential equation? A differential equation which can be shorthanded as diff-EQ is any equation that involves an unknown function and one or more of its derivatives. Now these can arise in real-world problems and problems in applied mathematics. It is often the case that finding a relation between a function and its rate of change is easier than finding a formula for the function itself. Now you should recall from calculus that there are two types of derivatives studied. We studied ordinary derivatives which are of the form dy dx or y prime of x. And then we also studied partial derivatives, which looked like partial f, partial x, partial f, partial y. This means that there are two broad categories of differential equations. We can have an equation involving only ordinary derivatives. These are called ordinary differential equations. Or ODEs. We can also have equations that involve the partial derivatives. These are called partial differential equations. Or PDEs. In this course, we are going to look at methods of solving only ordinary differential equations. The study of solutions of partial differential equations is a course in of itself. When looking at a differential equation, there are three quantities that often appear. We have the dependent variable, which is the function that we're trying to solve for. We have independent variables, and these are the variables for which the function is a variable of. So these are the function variables. And then we have parameters. These are just constants. Now, these constants remain fixed for any given problem. However, these constants can vary from problem to problem. Now you should also remember that when studying derivatives in calculus, we had higher order derivatives. We could take the first derivative, we could take the second derivative, the third derivative. In this sense, we also have an order of a differential equation. So we define the order of the differential equation to be the order of the highest derivative of the unknown function that appears in the equation. We can also have a special type of differential equation. We call this linear. So we say that an nth order differential equation is said to be linear if it can be written in the following form. A sub n of x times the nth derivative of y with respect to x plus a sub n minus 1 of x times the n minus first derivative of y plus so on and so forth plus a sub 1 of x times dy dx plus a sub 0 of x times y is equal to g of x. Where each of these ai's and g are functions of x, and y is the unknown function. Now, any ordinary differential equation not of this form is said to be non-linear. So an ODE not of this form is called non-linear. Let's now take a look at several examples of differential equations. So the first one we're going to look at is called the harvested population growth equation. It's P prime of t is equal to R times P of t, all times the quantity of 1 minus P of t over n minus h. So the first thing we notice is that this is a first order equation. The unknown function is p of t, and the independent variable is t. This leaves our parameters, which are r, n, and h. Next up, we have the spring mass equation. Which is given by d squared x d tau squared plus 0.9 dx d tau plus 2x is equal to 0. Now this equation is second order. The unknown function is x. The independent variable is tau. And there are no parameters. A third equation is an RLC circuit showing beats. This is given by I double prime of t plus 4i of t is equal to sine of omega t. So once again, we have a second order equation. The unknown function is I. The independent variable is t. And we have a single parameter, omega. Our fourth equation is the van der Pol equation. It's y double prime of t plus mu times the quantity y squared of t minus 1 all times y prime of t plus y of t is equal to 0. Now once again, this is a second order equation. The unknown function is y. The independent variable is t. And the parameter is mu. Finally, we have Laplace's equation. which is partial squared partial x squared of u plus partial squared partial y squared of u is equal to 0. Now, once again, this is second order, but this time it's a PDE. The unknown function is u. The independent variables are x and y, and there are no parameters. Now, any function, let's call it phi, defined on some interval I and possessing at least n derivatives that are continuous on I, which, when substituted into the differential equation, reduces the equation to an identity, is said to be an analytic solution. Or simply a solution of the differential equation on the interval I. This interval, this I, has several names. Right? Can be called the interval of definition, the interval of existence, the interval of validity, or the domain of the solution. Now, the graph of a solution is called the solution curve. Also, a solution in which the dependent variable is expressed solely in terms of the independent variables and parameters is called an explicit solution. Obviously then, this leaves implicit solutions. So a relation g of x comma y equals 0 is said to be an implicit solution to the differential equation f of x, y, y prime, so on and so forth, equals 0 on the interval I, provided that there exists at least one function, phi, that satisfies the relation as well as the differential equation on I. Now, let's look at how to show that a function is a solution to a differential equation. So the function we're given is p of t is equal to e to the negative 2t, and we want to show that this is a solution to the equation x double dot plus 3x dot plus 2x equals 0, where the notation x dot is defined to be the derivative of x with respect to t. It's a shorthand for that. So, take the first derivative of p. We get negative 2e to the negative 2t. Take the second derivative of p. We get 4e to the negative 2t. We now want to plug all three of these values into the equation. So we get 4e to the negative 2t plus 3 times negative 2e to the negative 2t plus 2 times e to the negative 2t. So what does this give us? We'll get 4e to the negative 2t minus 6e to the negative 2t plus 2e to the negative 2t. 4 and 2 is 6, minus 6 is 0, so this does indeed equal 0. So this choice of p satisfies the differential equation and is thus a solution to the differential equation. Now let's look at the function. Phi of t equals the square root of 1 minus t squared. And the equation x dot is equal to negative t over x. So as before, what we want to do is we're going to take the derivative of phi with respect to t. So what we get, 1/2 times 1 minus t squared to the negative 1/2. Then chain rule says multiply this by negative 2t. So this equals negative t over the square root of 1 minus t squared. But that square root of 1 minus t squared is phi. So it becomes negative t over phi of t. And notice that this is now the same exact form as the original equation. And so this satisfies the differential equation, and so we have a solution. If we go back real quick to the previous example, x double dot plus 3x dot plus 2x is equal to 0. Notice that x equals 0 would also be a solution to this. We call such a solution a trivial solution. So the trivial solution is a solution that is identically 0 on the interval. So just some more terminology for solutions. So a solution of the differential equation f of x, y prime is equal to 0. Containing a constant, call it c, is a set of solutions g of x, y, c equals 0. And this set of solutions is called a one-parameter family of solutions. If we're solving an nth order differential equation, f of x, y prime, yada yada yada, up to the nth derivative equals 0, we get an n parameter family of solutions. G of x, y, c1, c2, so on and so forth to cn is equal to 0. Furthermore, any solution that is parameter free is called a particular solution. We conclude by looking at a system of linear differential equations. This is simply two or more equations two or more differential equations of a single variable, independent variable. So a solution to a system is a set of differentiable functions on a common interval I that satisfy each equation of the system simultaneously. This part is important. If the set of functions satisfies every equation in the system except for one, it cannot be a solution. It must satisfy every single equation in the system. We're going to see this for a simple system and a simple set. So we have the set of solutions x of t is equal to e to the negative t, and y of t is equal to negative 4e to the negative t. And we have the system x dot equals 3x plus y dot is equal to negative 4x minus 2y. Now let's first find the derivative x dot of t. Well, this is just simply negative e to the negative t. Y dot of t is 4e to the negative t. So if we now take these derivatives along with our original set, we're going to plug them into each equation of the system and show that it satisfies both equations. So x dot is negative e to the negative t. This must equal 3 times x, which is e to the negative t, plus y, which is negative 4e to the negative t. So what do we get? We get 3e to the negative t minus 4e to the negative t. This is indeed negative e to the negative t. So this first equation in the system has been satisfied. Now let's check the second. So y dot 4e to the negative t must equal negative 4 times x minus 2 times y. So this is negative 4e to the negative t plus 8e to the negative t, which is indeed negative, I'm sorry, not negative, 4e to the negative t. Since both equations in the system are satisfied, this set, e to the negative t, negative 4e to the negative t, is a solution to the system. Now we have studied the basic terminology of differential equations. We will spend a good majority of this course finding solutions to ordinary differential equations. We will start by looking at methods of solution for first order. Then we will move on to the more general nth order equations, with a more heavy focus on second order. We will not look at finding solutions to systems until the end of the course. That is the end of this lesson. I hope you had fun. I hope you learned something, and we will see you in the next one.